Good afternoon. My name is José Torralba. I work at the University Carlos III in Madrid, Spain, and also in the Materials Institute in Madrid. And this work, entitled Development of a New Chromium-Based Hard Metal with nano-safe tungsten carbide grain size through liquid phase sintering and spark plasma sintering, has been made in collaboration with Dr. Deng from the Beijing Institute of Technology and Dr. García Junceda, also from the India Materials Institute. So this work is focused in the replacement of the cobalt in the conventional hard metals, tempered carbides, that usually use cobalt binder and usually tungsten carbide and other carbides as reinforcement. The market of these hard materials are really high, high amount of the percentage of the total consumption in the global metal cutting market. So what we want to do is to replace cobalt. Why is interesting to replace cobalt? Cobalt has some drawbacks, which we can see here. The historical price of the cobalt is increasing in the last year. Also, cobalt has some levels of toxicity and limited availability. Cobalt today is considered since 2020 by the European Union as a critical material, both in terms of price and availability. It can be seen in this European Commission study that was published in the last year. So it could be interesting to replace cobalt, but the problem is that the cobalt is the best binder for the cemented carbides due to the good combination of cobalt with the tungsten carbide during the sintering. So in our case, we want to design a novel tungsten carbide chromium-based metals without cobalt or nickel, that also has some problems of toxicity and price. And we have to replace the conventional, the idea is to replace the conventional tungsten carbide cobalt hard metals in some specific application, not of course in all the applications. Another field that we want to explore is to work with particles of very small size in order to obtain the so-called nanosite hard metals, as you can see here. In this graph, we can see how the fractal toughness usually is reduced as much as we increase the hardness of the cemented carbide, but only if we use nanosite hard metals we can maintain some level of fractal toughness, even increasing the level of the hardness. The problem is that with the temperature, the tungsten carbide grain size increases strongly with the temperature. So we have to produce these nanostructured hard metals, which is a technological challenge, because the rapid growth of the tungsten carbide with the temperature avoid to maintain the hard metals in this group of the so-called nanosite hard metals. For this reason, it could be interesting to go to sintering techniques that avoid the grain growth during the sintering. So in our case, we want to design these nanostructured chromium-based hard metals with good performance and low cost, in which we replace the cobalt by chromium or iron. That chromium and iron has lower price, less toxicity, is more available in the market, and it could act as a tungsten carbide grain size inhibitor, and that will contribute to don't lose so much fractal toughness. In that sense, despite we will test also materials with liquid phase sintering, we propose to use spark plasma sintering as a technology to consolidate these hard metals, because with this technology we can reach high levels of density in a very fast sinter cycle with good microstructural quality and stability and good mechanical properties. So the methodology is to use to design the composition using this chromium iron binder, but through thermodynamical simulation we have decided to introduce iron, because iron can reduce some negative, can improve the densification of these cemented carbides, and also carbon in some specific amounts in order to reduce the formation of some negative phases that can be produced during the sintering process. So this combination of iron and carbon will be in some way predicted by thermodynamical calculations, mathematical simulations, and then we will develop the bulk materials by spark plasma sintering, and we will analyze the microstructure and the properties. In this case, we will see the hardness, the fracture toughness, and we have some results also regarding the wear resistance and the oxidation resistance of these new hard metals, of these new hard metals. The starting powders that we have used are two different families of powders, of cemented carbides of a small size. Here you have the particle size distribution of this tungsten carbide, and also we have used chromium iron powders, the percentage of 75 of chromium, 25 of iron as balance, and in this case, this powder was supplied by Höganäs in Sweden. So the chromium iron powders are more irregular than the tungsten carbide, which is more spherical ones, and due to the small size of these particles, used to tend to be agglomerated. As carbon and extra iron powders, the iron powder that we have used are carbonyl iron powder, supplied by William Rowland Limited. This powder is quite fine powder, very small size powder, and this will contribute to increase the sintering behavior. The carbon is natural carbon, is added in principle to avoid the formation of theta phases, and this carbon is also a conventional carbon used in conventional powder metallurgy. So the first step is to integrate the carbon or the iron in or also the iron chromium binder with the tungsten carbide powders, and we did it by mechanical milling. These are the mechanical milling conditions that we have used. The ball to powders ratio is 10:1, and here we have the amount of tungsten carbide and iron chromium that we have used. We have used stearic acid as a control process agent, and we have used also argon in order to avoid oxidations. We have tested different milling times. In the next slide, we can see the evolution of the morphology of the powders through the milling time, and at the end we have selected the 20 hours milling time in order to have these rounded powders for the consolidation process. So with the mechanical milling, we usually have this effect that we increase the internal microstrain and we reduce strongly the crystalline size. Reaching this small crystalline size, we can expect to have at the end this so-called nano size cemented carbides that we are looking for in order to don't reduce too much the fracture toughness with increasing the hardness. We have prepared some bulk materials through liquid phase sintering with these conditions. We heat it up till 1450 degrees for 30 minutes and furnace cooling in argon atmosphere. And we have selected this temperature because it's about 100 degrees above the eutectic temperature of the tungsten carbon chromium system. These materials reach a relative density near to 96% in the case that some iron additions, but as I mentioned before, we have combined iron additions and carbon additions in order to increase the sinterability of these cemented carbides. And as you can see here, using in the order of 3% of iron and 0.5% of carbon, we can reach the lowest average tungsten carbide grain size in the final bulk material with good levels of relative density. Later we will analyze a little bit better microstructure, but also the hardness that we can reach adding these amounts of iron in combination with some amounts of carbon. You can see here with this combination of 3% of iron and 0.5% of carbon can reach good levels of toughness, but not so high if we compare later with other materials obtained by spark plasma sintering, but the highest levels are in these amounts of carbon and reaching also good levels of hardness. Here we can see that the spark plasma sintering method. Here we have the typical force displacement time diagram, and with the field assisted sintering, we use much lower sintering than the conventional sintering temperature. So in principle, this will avoid the grain growth of the tungsten carbide. It's a fast sintering process. We can, in this way, obtain a much proper microstructure, looking for a good final fracture toughness combined with good hardness. We have tested many spark plasma sintering conditions. As you see here, we have changed the heating rates. We can even test different temperatures, 1200 or 1350 centigrade degrees, and different times and different pressures. At the end, we have selected for our best material, our best combination of material, which is the 3% of iron with 0.5, 1 or 2% of carbon, the highest temperature, the heating rate of 400 degrees per minute, for a holding time of 10 minutes and a pressure of 80 megapascals. This holding time with this high speed, high heating rate allows to us to get a good densification. As you see here, the best densification was obtained by the value of 3% of iron and 0.5% of carbon. This is this graph with the black line here. The pink one is regarding the 2% of carbon, and this one is regarding to the 1% of carbon. So the best combination of elements, iron and carbon, is 3% of iron, 0.5% of carbon, reaching the highest level of density. So this is the microstructure that we obtained just for the tungsten carbide with the chromium-based hard metal, without any addition of iron or carbon. And you can see here that we have the binder. This is the binder face, the black one, and this is the tungsten carbide, the white one. And analyzing the compositions by STEM EDX, developing an STEM EDX maps, we can see some chromium oxides also in between the tungsten carbide and the chromium iron binder. So if we introduce iron, we have the presence there not only of the chromium oxide, but also the formation of this iron tungsten carbide that in some way is better than the eta phase, because this carbide in some way prevent also the growing of the chromium oxide and allows to reach good levels of toughness. Here we have some of the results regarding of the relative density and the average tungsten carbide grain. Also in this graph on the left, you can see how the amount of the level of the grain size decrease with the increase of iron. So it could be a good idea to try to combine the carbon with these high levels of iron. So we have selected 3% of iron, and we mix with this 3% of iron different contents of carbon that we will analyze later. So here you can see also the toughness that we can reach with this 3% of carbon, and you see that we have increased a little bit the toughness that we got with the liquid phase sintering, that was lower than this value near to 6. So also the hardness can reach some high levels, and from these values of 3% of iron, we had different contents of carbon. Previously, we have tried to see what happens in terms of the possible carbide formation with addition of carbon to the tungsten carbide. We have tested different. Later, we will test different amounts of carbon between 0.5% and 2%, but the highest levels of addition of carbon can produce the formation of graphite, which is not a good idea in terms of the final properties. So later we will see that the best combinations are near to 0.5% of carbon additions. Here we have the evolution of the mechanical milling. At the end, we got also after 20 hours of milling, these rounded particles. The microstructure with the different carbon additions also presents some levels of chromium oxide, but as much as we increase the amount of carbon, we can have also these carbides which are not desired due to the brittleness that can be introduced with this percent of carbons. Here we have also, with more detail, what is happening in the microstructure with an extra amount of carbon over 1% or 2% with these new carbides that can be established. Here we have the relative density that we can reach and the average tungsten carbide grain that we can reach with a combination of 3% of iron and 0.5% of carbon. And you can see here how this combination of iron and carbon with the new binder can allow us to reach the lowest level of the tungsten carbide grains and the highest level of relative density. And also, if we analyze the properties by the indentation method, the fracture toughness of this material can reach levels of 8 or 8.5 megapascals per meter, and relatively high levels of hardness over 2200 beakers. So these values, this is the optimized material, can be plotted here in this graph, in which we can correlate the tungsten, we can correlate the fracture toughness with the hardness, and we are just in this point that can be, we can compare our result with some conventional tungsten carbide with cobalt, conventional hard metals. Here we can compare the difference that we reach with the spark plasma sintering samples with the liquid phase sintering samples. The average grain size is much higher in the liquid phase sintering than the spark plasma sintering, and that allows us to have much higher hardness with a good combination of fracture toughness. Also, we have developed some wear resistant tests. We have done it in a Baker tribometer in a dry sliding test with the system of ball on plate. We have used alumina balls, and here you can see the profiles of those tracks in the material. But if we measure the wear loss, the wear rate in comparison with conventional cobalt-based hard metals, which is here on the right in green colors. Here we have on the left our results, and the material that we have selected as the best one with 0.5% of carbon and 3% of iron got the best results in terms of wear rate, the minimum wear rate in comparison with all the other materials. And also we have tested the mass gain in terms of oxidation, and we have compared our material, which is those on the bottom part of the graph. The red one is the material with 0.5% of carbon and 3% of iron. And here in this pink color we have some, and this green color we have some conventional cemented carbides, and we have seen that the growth of the mass gain growth in comparison with our materials is much higher in the other conventional cemented carbides. So that means that we are getting a good combination of oxidation and wear for this material. So this is just a comparison in between all of them. So as a conclusion of this work, and trying to be on time, we can say that the spark plasma sintering is a suitable technique to consolidate these novel tungsten carbide chromium-based hard materials with very fine microstructures and good mechanical properties. The addition of iron and carbon improves the toughness hardness relationship in these hard metals, and if we put only iron, can induce the formation of eta phase, which is brittle and we have to avoid, but the addition of carbon can reduce these amounts of eta phase and can allow us to get a good combination of properties. So this, the processing, the viability of processing of this novel chromium-based tungsten carbide hard metals by mechanical milling and spartanicity with optimal hardness and toughness, relationship and good oxidation and wear resistance has been demonstrated with this research work. And this good combination of oxidation resistant and wear resistant values might lead to the future replacement of cobalt-based tungsten carbide hard metals. So those applications are promising, and I think we're opening. It's open a new way to develop new families of materials, avoiding the use of cobalt. So thank you very much for your attention. We have to thank also the China Council for the grant received by one of the members of the team of the group. This is also the help of the research group, the Powder Technology Group in the University Carlos III of Madrid, and also this technological center from Poland that allows to us to develop the spark plasma sintering bulk materials, and in Hyperion, in Spain, the Spanish branch of Hyperion, we developed the wear test. So thank you to all of them for their assistance to us, and thank you to you for your attention.